Hi everybody, this is Dr. Bricker here with a video for chapter 24. This is part 1. So chapter 24 is a rather long chapter. First it deals with sources of magnetic fields, and then the latter part of the chapter deals with what happens to a moving charge in a magnetic field. Sometimes physics textbooks actually make this 2 chapters. Here it's 1 chapter, but it is a rather long chapter. So this is part 1. So we're transitioning from electricity into magnetism. And in the next chapter, chapter 25, we'll see that one is really the other side of the coin um, from the previous one. For example, electricity, you could make a magnetic field with it. Magnetic field, you could make electricity from it. So that's coming up in the next chapter. Okay, so this chapter does deal with how magnetic fields, we learn about magnetic fields and then the effect of magnetic fields on moving charges. So with electric fields, the charges don't have to be moving for there to be a force. If you have an electric field and you have a charge in it, in the electric field, you'll see a force. With magnetism, the charges have to be moving in the magnetic field. If there's no movement, there's no force. There also has to be an angle between the magnetic field and the force for there to be a magnetic force. So it's some similarities, but some big differences as well. Okay, so a compass is a magnetic dipole. So thinking back to electricity, a dipole was a positive negative charge separated. We had a dipole. With magnetism, magnetic fields only come as dipoles. You always have sort of a north and a south. With electricity, you could have a positive charge by itself. You could have a negative charge by itself. With magnetism, it doesn't work like that. You always have a north side of a magnet and a south side of a magnet. The north side is kind of acts like a positive charge, the south side like a negative charge. Okay, so magnets are a nice tool to use to actually plot out magnetic field lines. And here's a ring, and you can see there's some iron filings around here. So there's current going through this ring, and because there's current moving current actually produces a magnetic field. So moving current produces a magnetic field, and you can see the shape of it here. So we're going to learn some tools to describe these different shapes. So there's something called the first right-hand rule. We'll deal with this, and then the second right-hand rule will tell us the direction of the force. Okay, so the thing about magnetism, it's always working in 3 dimensions. So we're going to have to start getting used to thinking about space as a 3-dimensional construct instead of just a 2-dimensional, which we've so far have done. Okay, so maybe some of you have actually seen this. This is the northern lights here. So charged particles come from the sun. They're heading towards the Earth. Luckily for us, the Earth has a magnetic field. The magnetic field exerts a force on these charges, causes them to spiral to the poles. So that sort of filters them out. If we did not have a magnetic field, over time our atmosphere would be completely blown away. That's what's happened, not completely, but almost completely blown away. That's what's happened on Mars, actually. So luckily for us, we have a magnetic field. Not only can we see this beautiful picture here, it protects us from these charged particles moving towards us from the sun. Okay, so we'll see how that works out. Okay, so the first section is on magnetism here. So here's a couple of experiments that we're going to take a look at. Experiment 1. If a bar magnet is taped to a piece of cork, and you see the north side and the south side of the magnet there, and it's allowed to float in a dish of water, it turns itself to a line in approximate north-south direction. Not completely, but pretty close. The end of that magnet points north is the North Pole. So the North Pole of the magnet, the other side is the South Pole of the magnet. So the Earth has its own magnetic field, and this little bar magnet here is aligning with the Earth's magnetic field. So a magnet that's free to pivot like this is just called a compass. Maybe use a compass for some navigation. Okay, so really a compass just is a bar magnet, and it's in this liquid here, so it could rotate around easily. Here's another experiment. Here's a couple of like poles, and you've probably experienced this in your own life. If you take a couple of magnets and you kind of try to stick them together, sometimes they repel each other. So the 2 north sides of a magnet will repel each other, as you can see here. Also, 2 south sides of a magnet will repel each other. The electricity analog to this would be 2 positive charges don't like to be by each other. 2 negative charges don't like to be by each other. So the same a similar thing happens with magnetism. On the other hand, a north side of a magnet and a south side of a magnet will be attracted towards each other. So just like opposite charges attract, opposite poles of a magnet attract. Here's another experiment. So we're building some characteristics of bar magnets here. If you cut a bar magnet in half, you might think that you can get a north side and a south side. You don't. You just get two smaller magnets. And you can keep doing this and doing this and doing this, and you'll keep getting a north and south side. Now with electricity, if you had a positive charge and a negative charge, obviously you could move those away from each other. You could have a isolated positive charge, isolated negative charge. You can't do that with magnets. You always have a north and south side. Okay, so that's a big difference between magnetism and electricity. Here's experiment 4. Magnets can pick up objects like paper clips that are not even magnetic to begin with. Over here, though, we cannot pick up a penny. We can't magnetize this. So essentially what you're doing here, when you're able to pick up a piece of metal like this, like the paper clips, you're magnetizing for a short amount of time the paper clips. So the magnetic field of the bar magnet here magnetizes the paper clips, and then they can actually stick together. Same thing over here. You're not able to do that with a copper penny here. Okay, you can't do it with other materials either. Aluminum, glass, plastic, you can't magnetize that. It has to do with the structure of the iron here. So this external magnetic field from the magnet induces the domains, as it's called, of the metal here and the paper clips to align with each other and make this thing magnetic. Okay. Here's another experiment. When a bar magnet is brought near an electroscope, so an electroscope is an object that you could actually charge up. So if you were to charge this with charge, these little gold strands here would actually separate. But if you bring a bar magnet near the electroscope, nothing happens. So you can't charge this up with a magnet in this way. You could if you had a plastic rod or a glass rod like we saw in chapter 21. Okay, so you can't induce this thing to become charged up by just bringing a bar magnet close by. So what do these experiments actually tell us? Not the same as electricity, but there are some similarities. And again, in the next chapter, we'll see that you could make one from the other. Okay. So magnetism is a long-range force. What does that mean? The magnets don't actually have to be in contact with each other. Just like charges don't have to be in contact with each other for them to experience a force on one another, magnetism is the same way. It's a long-range force. Things don't have to be in contact. Okay. Magnets always have two poles, north and south. So we always have a dipole situation with the bar magnet here. Okay. The difference would be with electricity. You could have an isolated positive, isolated negative charge. Okay, so the poles of the bar magnet can be identified and used as a compass. So usually if you do have a compass, one side has a different color than the other side. Usually the brighter color is the one that's going to point north. So if you're trying to navigate, you can use that as an indication of the direction that you're traveling. Okay. And we'll see why that it points north in just a few minutes. Only certain materials are magnetic. One of the most common is iron. And, maybe you even have some of these sort of magnets on your refrigerator. They're not quite bar magnets, but it's the same idea as a bar magnet. Okay, so here's one that we could check here. Bar magnet is cut in half. What do you end up with? So we saw this. You end up not with this. If you weren't taking physics, you might think it's this, a north and a south. But it's not. You get two smaller magnets. You get a small one that looks like this. Whoops. And another one that looks like this. Okay. That's sometimes ends up as an exam question, so keep that in mind. So what does a magnetic field look like? Well, every magnet sets up a magnetic field in the space around it. Just like charges set up an electric field, we saw before it was defined as for a positive charge, the electric field went away everywhere. For a negative charge, the electric field went towards it. And if you put those together, you got a dipole where you would see it going from the north side to the south side. With magnets, magnetic field lines leave the north side just like they left the left the a positive charge, and they go towards the south side of a bar magnet. Okay, just like electric field lines went towards a negative charge. So the north side of a magnet acts sort of like a positive charge. The south side of a magnet acts like a negative charge. Now, if you put a dipole in an external magnetic field, so that's what we're seeing here. Here's a positive charge here. Here's a negative charge here. Oh, sorry. These are electric dipoles. See, they're almost the same thing. Here's an electric dipole, positive and negative, and you put this into an external electric field. This dipole will tend to line up with this electric field. So if electric field's pointing this way, so if the electric field's pointing up, the force on a positive charge would be this way. So it goes that way. The force on a negative charge would be back down this way. I'm just giving you the direction of the force. So this dipole would want to line up with the electric field because there's a torque on this dipole. So the torque caused by an electric field tends to align the axis of the dipole in the direction of the electric field. And it says here the torque on the dipole is greater when the electric field strength is greater. So that, again, goes back to chapter 21. We just saw that. So, F is equal to Q times E. So if you have an electric field and you have a charge, there's going to be a force on it. The dipole, because there's a force, experiences a torque and lines up with the electric field. The bigger the electric field, the bigger the force, and therefore the bigger the torque. Now, the same thing happens if you put a bar magnet, or in this case, it looks like a compass needle, in an external magnetic field. So B is used for magnetic field. You might think it should be M. There's something else that's used for M. So here we have B for magnetic field strength. So here was the compass. This is the north side. This is the south side. The magnetic field points up this direction. So there's going to be a force on this needle and therefore a torque. So that the compass needle lines up with the magnetic field lines here then. Okay, so really similar to what we saw with the electric dipole in an electric field. This is a magnetic dipole in a magnetic field. Okay, good. So B, again, used for magnetic field. Just like the electric field, it is a vector quantity and represents the magnitude and strength of the field. So magnetic field strength is measured in Teslas, T-E-S-L-A, for probably the famous scientist you heard of, Tesla, not named after the car company. Just kidding. The direction of the magnetic field is in the direction of the north pole of a compass, really similar to what we saw with electric fields before. And the strength is proportional to the torque felt by the needle. So the bigger magnetic field would cause a bigger torque, just like bigger electric field caused the bigger torque in the electric scenario. Same idea. It's nice when we did electric fields, now we're doing magnetic fields. One sort of builds on the other, so we have a little bit of a foundation of the concept, I think. Okay, so how do you measure the magnetic field? You could measure how much these are going to actually be deflected. And we can measure the direction by just taking a compass needle and putting it around this this bar magnet here. So remember, this is going to line up with what the magnetic field lines look like. So here the magnetic field line must point just like this, like they're showing you here. Here the magnetic field line must be pointing this way. The highlighter's going a little crazy. But here's where the magnetic field is there. Here's where the magnetic field is here. If the field is weaker, it's not going to turn as strongly, so it's a little weaker over here. It's stronger here because we're actually closer to the magnet. So that's what it's showing you here. The closer you get to the magnet, the stronger the magnetic field strength is. And when you're over here, it's a little bit weaker. Okay, so you could take these compasses and put them all along where this magnet is and plot out the magnetic field lines. Now, if this were an in-class lab, we actually do this. We have a bar magnet. We take these compasses and we put them around here, and you can plot out where the magnetic field lines end up. There's some iron filings here just to kind of illustrate what they look like. So the closer you are to the bar magnet, the bigger the strength, and they go from the north side to the south side. So notice the red part of the compass here pointing that way. If you went all the way around here, the needle would keep turning like this. So the Earth has a magnetic field. This magnet has a magnetic field. Really, there's two magnetic fields. The magnetic field, because of this bar magnet, is a lot greater than the Earth. So we're essentially seeing just mostly here the magnetic field of the magnet, of this bar magnet. Okay, so a magnetic field of this magnet points away from the north side and then into the south side. And the same thing is happening with these little iron filings. So the iron filings become magnetized. They're little compass needles in their own right, and that's why they line up like this. Okay, where the strength is strong, the torque easily lines it up. The farther and farther you get away, the less and less the strength. Things become less organized, and the filings barely line up when you get really, really far away. You can see here, this is starting to get over here a lot less populated and a little dimmer. Here, though, they're really sort of activated the closer you get. Okay, so the magnetic field vector representation is useful, just like it was when we did electricity. It helped us to solve some problems. Okay, if we want the overall representation of the field, magnetic field lines are just sort of a way of thinking about it. Okay, so you have a bar magnet. You don't see these things. They're sort of a human-made idea, but it helps us visualize what's going on. Okay, here's maybe a sort of an animation way of looking at it. This isn't a real magnet, but if you did this, you'd see like the needles are lining up, so the magnetic field is going this way, from the north into the south. So we're going this way. Okay, so again, the north side kind of acts like a positive charge. The south side sort of acts like a negative charge if you had an electric dipole. So let's see. A compass is placed at the black dot. In which direction will the compass point? Okay, so we've got a bar magnet here. Here's the north side. So always from the north side, the magnetic field points away. The south side it's going to point towards. So if you were to take a compass and you put it here, which direction would the compass needle point? It's definitely not 0 because we have a bar magnet here. I don't know if you can see this well, but it's got to be pointing away, right? If you put a compass right here, which way would it point? It would have to be pointing away because we know magnetic field lines leave the north side and go into the south side. Okay, what if you put a compass up here at this point? Which way is the needle going to point? All right, so we know magnetic field lines leave the north, wrap around here. So here we're going this way. And then they end up at the south. So if you were to take a compass and put it up here, it would have to be pointing that way. So pointing towards the left. And then now if you were able to do this for more and more and more points, you could build a picture of what the magnetic field lines would look everywhere. So if you're here, it's always going to be pointing to the left. If you're out here, like we did in the first one, it was pointing that way. If you were to figure out what it looked like here, put a compass there, it's actually going to point this way. Okay, good. So I'll just go through these quickly. The direction of the magnetic field line at any point. Well, it's tangent to this curve here. So here's the curve. Here's another curve. It's tangent to that curve. So when the magnetic field lines are closer together, the strength is greater, as it says here in number 2. So the closer and closer you get to the bar magnet, the bigger and bigger the magnetic field lines, or the strength is, these lines are closer together. Okay, and in number 3 over here, leaving the north side and going into the south side. Okay, excellent. So a single bar magnetic field lines start on the north side, so the red is the north side here, and then they end up here at the south side. And when you go farther and farther away, the strength gets less. So here's an actual picture. And then here's what it looks like if you include magnetic field lines. The closer you are, the greater the strength. When you go farther and farther away, for all practical purposes, it becomes 0. Okay, but when you're close, it's really big. And then here's a closer picture of this. So this is just focusing in on the last slide. Same idea. Leaving the north, going into the south, closer together. The lines, when they're closer together, the strength is greater, which means you're closer to the magnet. Okay, so what if you took a couple of bar magnets and put them together? You can figure out the net magnetic field. So here's the north side, here's the south side. So in between here, the magnetic field lines coming out of the north would be to the right. The magnetic field lines, because of the other magnet, would be going also to the right because they're going into the south side. So in between here, those are sort of working together. Now, the analogous situation would be if you put a positive charge here and a negative charge here, and you wanted to figure out the electric field between them. You'd have to add the contributions together. We actually had, we did some homework problems on that, and exam 1 had a problem like that. Figure out the net electric field right between the charges. Okay, so in that case, on the exam, we had to add those together. Same thing here, we have to add those together. Okay, very good. So we look at the contribution from the one magnet, from the other one, and then we figure out the net contribution. And it might look something like this. And here's the physical proof of that. So what happens if you put like a north and a north together, like you have here? Well, the analogous situation would be, what happens if you put a positive charge and a positive charge close together? Well, in between, if this were a positive charge here on the left, the electric field would be to the right. If you put a positive charge here, the electric field would be to the left. Right in between, they actually cancel out. So here you're seeing nothing right in between them because they're canceling out. One is to the right, one is to the left. So I started talking about positive and positive charge. It's the same idea, though. North side of a magnet, north side of a magnet. That sort of acts like two positive charges. So right in between, they're canceling out. Okay, so this might be something like a refrigerator magnet, a bunch of horseshoe magnets. So maybe you've experienced these before. North-south, south-north, north-south, south-north. And you can look at the magnetic field due to this. So same idea, we're leaving the north side and going into the south side. So you see something like that, something like this. Same idea, leaving the north and going to the south. So magnets can have, it says here, more than one pair of north-south poles, and the poles do not need to be at the ends. So what if you took a magnet and you bend it into the shape of a horseshoe? You'd get something that looks like this. And a good example of this is a refrigerator magnet. This is a side view of what's really going on. So you have your fun refrigerator magnet. Did you realize it was really a bunch of horseshoe magnets all hooked together like this? Okay, so the south pole of the Earth's magnet is located, but not exactly coincident with the north geographic pole of the Earth. So what we call the north geographic pole is actually the south pole of the Earth's magnet. If you thought about the Earth as having a big magnet in it, let's actually take a look at the picture of that. So here's the Earth. The south magnetic pole is not quite lined up with the Earth's actual geographic pole. It's off by a little bit here. But as far as the magnetic field lines go, we're leaving the north side and going into the south side. That's why when you take a magnet, or a compass that has a little bar magnet built in, if the magnetic field lines are going like this, the compass needle will want to align with the direction of these magnetic field lines. So the magnetic field lines are pointing from the magnetic north to the south. So if you take a bar magnet and you put it in this magnetic field, it's going to line up. That's why it points north. I should say maybe north-ish. So sort of a neat idea. I think your intuition would be, well, it's the North Pole. That's where the north part of the magnet is. But it's actually the south part of the magnet. That's why a compass needle will line up and point north. It's actually pointing to the south magnetic pole. What do we have here? These magnetic bacteria have strongly magnetized bits of iron in their bodies, and their bodies rotate to line up parallel to the Earth's magnetic field, just like compasses. And these bacteria prefer a low oxygen zone near the bottom of water. So if the water is disturbed and they are displaced upwards, they follow the vertical component of the Earth's magnetic field downward. Many animals in nature use this idea. So there's a group of little sea turtles. They're born on a beach. They run towards the ocean. Most of them don't make it there. They're eaten by birds. But the ones that do make it there swim their entire lives and make it back to the exact same beach they were born on. And this is after going swimming in the ocean thousands of miles away. How do they know to get back? So scientists think they use the Earth's magnetic field to navigate and make their way back. So some might say that's intuition. Well, maybe it's a little bit of intuition, but the intuition is based on something. It's this idea of using the Earth's magnetic field to go back to where they were born. They probably don't think, "Oh, I'm going to use the Earth's magnetic field," but that's what's going on. So we looked at bar magnets, the Earth's magnetic field, and we can also make magnetic fields by having moving current. So compass will react to a bar magnet. We saw that so far. Compass will also react to current in a wire. So if you have current going through a wire and you put a compass nearby, the compass needle will line up with the magnetic field created by moving current. Okay, so again, the first part of this chapter is ways that we can produce magnetic fields. We've got bar magnets, moving currents. The next part of the chapter is what happens to a charge in a magnetic field. So we're still working on the part where we're creating magnetic fields. So electric current produces a magnetic field. The shape of the field depends on the shape of the current carrying wire. This is where the first right-hand rule will come into play. So here we have current in this wire. The current's actually flowing upward, and the magnetic field lines would be all around it. So if you took a compass and you put it near here, the magnetic field lines wrap around this current. So this is where you have to start thinking in 3 dimensions. So here's a kind of a different view. Here the current's actually coming out at you. So the current is coming out of the screen, and the magnetic field lines are wrapping around. So at this point, if you were to put your thumb in the direction of the current, which is coming out of the screen, the rest of your fingers wrap around the direction that the magnetic field would be. So do that. Put your thumb in the direction of the current, which is out at you, and then the rest of your fingers curl around in the direction that the magnetic field would be. Now, if the current were into the screen, you'd have to flip your hand around, and then current going into the screen, magnetic field lines would go in the opposite direction. Okay, I think there's a better picture coming up of that in just a second. What if you took this wire and you made it into a circle like you've done here? So you see this here at the top, the current's coming out at you, and then at the bottom it's going back in. Same thing, you can put your thumb in the direction of the current. So up here at the top part, current's coming out at you, magnetic field lines are going counterclockwise. Here it's the current's going back into the screen. So if you put your thumb into the screen, magnetic field lines would be going in this direction. So same thing, we had a straight wire before, this is a curved wire. Here's another thing that we'll take a look at in this chapter. A solenoid, a series of loops here, and this will produce a magnetic field. Now, previously with electricity we had capacitors. That was a nice way to get a nice uniform electric field in between the plates. A solenoid is a device where you get a nice uniform magnetic field right here inside the solenoid. There's still a magnetic field outside, that's still there, but the magnetic field inside is much greater, as you can see in this picture here. So we'll come up with the formula for solving for the magnetic field inside the solenoid. Okay? And the analogous relationship to electricity would be a solenoid sort of plays the role that a capacitor played before. If you ever had an MRI and you were inside the MRI machine, you were really in a solenoid here. Okay, so magnetic field lines due to currents have no start or end. Really the same thing was true with the bar magnet. We didn't see the picture inside, but inside the bar magnet there's still magnetic field lines. So we always have closed loops. That's how magnetic field lines work. So here's current flowing upward, and you can put your thumb in the direction of the current, and the way that your fingers go then That's the way that the magnetic field line goes. So it goes in a complete circle around here. If the current's flowing down, same thing, put your thumb in the direction that the current's flowing. So the current's going down, magnetic field lines are going around like this. This was actually discovered accidentally. Somebody just happened to have a compass around a wire. They turned on the power, current started flowing, and the needle deflected. Like, oh, okay, that was a nice accidental discovery. Okay, so here's maybe a better picture. Put your thumb in the direction of the current, and then the magnetic field lines curl around. So that's the first right-hand rule that we have. Now we're going to be dealing with 3 dimensions, so if you have a piece of paper in front of you, you might say north, south, east, and west on a piece of paper. But now we also have up and we have down. So there's 3 dimensions. I guess you could say also like east, west, north, south, and then up and down. So if something's pointing into the page, we represent that as arrows, and it might look something like this. Just like an X, that means into the page. Out of the page looks like this, so it's just dots coming out at you. The way people used to talk about this, if somebody shot an arrow at you, this would be like the head of the arrow coming out at you. That's what you would see. Or into the page, that would be sort of the feather part of the arrow. Okay, so this dot means out of the page, this means into the page, because we have to keep everything straight, right? There's 3 dimensions now. Okay, so using this new notation, you see the crosshairs here. That means the current's into the page. So if you put your thumb in the direction of the current into the page, the magnetic field lines are wrapping around this way. Okay, let's see. A long straight wire extends into and out of the screen. Let's see. A long straight wire extends into and out of the screen. The current in the wire. Oh, okay, so based on these compass readings, as you see here, we want to figure out which way the current is flowing. Okay, so we got to test it out and see what works. Let me say it's out of the page. So if it's out of the page, my thumb is in the direction out of the page. And then the magnetic field wraps around like this. That actually works out for me. So it's got to be out of the screen. The reason is from the right-hand rule. I lined everything up, and that's what I got. If it were into the page, the magnetic field lines would go the opposite direction, and that's not what we have here. And we definitely do have a current because these magnets are nice and lined up. Okay, let's see what we have here. Point P is 5 centimeters above the wire as you look straight down at it. Okay, so you're looking down at the wire. Point P is not on the wire, it's above the wire. It just looks like it's on the wire from that perspective. And we want to know which direction is the magnetic field at point P. Okay, so you got to move your hand around somehow. Hopefully you can see this okay. If the magnetic field, if the current is flowing to the right at a point above the wire, the magnetic field's got to be pointing down. Right, so line this up, put your thumb in the direction of the current, and then imagine the point that's above the wire. Which way is the magnetic field lines pointing? Well, they're going all the way around. Tangent to the path there would be down. By down, I mean this way. So at a point somewhere 5 centimeters above the wire, we have a circle. Tangent to the circle will be pointing down. And then we'll come back to this one when we get a little bit more information. Now, what if you took this wire and you made it into a circle like you see here? So this is a current loop. So current is flowing this direction. If you wanted to look at like sort of a slice of this, you could do that. Remember, this means out of the page, right at you. This means into the page. And you wanted to figure out the magnetic field lines maybe inside the loop. We're going to have 3 situations where we can actually calculate the magnetic field. A long straight wire. We haven't seen the formula yet, but we will. And here's another one, this current loop. We'll be able to calculate the magnetic field right in the center of the current loop. Now, you can calculate it anywhere you want to, in theory, and if you took a calculus-based version of this class, you would be able to do that. But for our purposes, we'll be able to calculate the magnetic field right in the center. First of all, though, which is the direction of it? We'll still use the right-hand rule to figure out the direction of it. Same idea, put your thumb in the direction of the current. So here's the slice view again. Your thumb is in the direction of the current, which is out at you, and then you can put your curl your fingers around, and that's the direction of the magnetic field. You can take your hand here and move it all the way around the loop. And when you do that, you'll see like in the center of the loop, the magnetic field's actually pointing this direction. If you took the same view here and looked at it with your eye over here, so your eye is looking at the loop from over here, you'd have this view. So everywhere in the center, it would be coming out at you. Okay, good. So take your hand, go all the way around this loop. No matter what you do in the center, inside the loop, I should say, the magnetic field's pointing out at you. And then it's wrapping around, and outside the loop, it's pointing this direction. So the formula that we'll come up with is the magnetic field right at the center of the loop. Okay, let's take a look at this one. The following diagram shows a current loop perpendicular to the page. Okay, so this is our new notation. This means out at you. This means into the page. So the current's coming out at you, going around the loop, and then going back into the screen. And we want to know, what is the magnetic field at this point? The direction of the current is shown. What is the direction of the magnetic field at the center? Okay, so that looks just like what we just did, coming out at you in the center. If you use the first right-hand rule, it would be to the right. So current's coming out at you everywhere as you go around the loop. It's pointing to the right, just like the picture from the previous slide. Okay, there are many applications of magnetism for which we would like to generate a uniform magnetic field. Just like with electricity, we had a capacitor to generate a uniform electric field. When you do that, you get a nice constant force. A field that has the same magnitude and same direction is a uniform magnetic field. So not only does it have the same strength, it has the same direction. A solenoid is a device where we can get a nice uniform magnetic field right inside this coil here. Okay, so there's current flowing through here. The way to think about this is all these loops, they're really close together. They're insulated from each other. So maybe you've seen something like this. It's sort of like a bright orange thing because it's made out of copper, a whole bunch of loops. If you really examined it, you see there would be a little coating on these wires, so they're not actually touching each other. That's what this, there's some space in between these. Okay, so this is another shape where we'll be able to calculate the magnetic field right inside here. Okay, and that's a solenoid. So it's the same idea. Here's a bunch of loops really packed together. Current's coming out of the loop, going back into the loop. Here's the magnetic field in between. So everywhere in between, these are all working together. That's why you get a big magnetic field in between. And then outside the loop, if you use the right-hand rule, you'd see the magnetic field outside is a lot smaller. We're concerned with the magnetic field in the loop, and that's the situation where we'll have a formula for that. Okay, so what is the direction of the current in this solenoid as viewed from the top? Okay, so if your eye is up here at the top, which is the direction of the magnetic field? Or sorry, what is the direction of the current? They're telling you the direction of the magnetic field. The magnetic field is up. So we want to figure out which direction the current is flowing. So you have one of two choices. It's either going clockwise or counterclockwise. So you have to use the right-hand rule. Just pretend it's going, let's pretend it's going this direction, clockwise. So let's pretend the current is going this way. So if the current were going that way, I'm putting my thumb in the direction of the current, inside the loop it would be pointing down. So it can't be clockwise. Now if it were going the other direction, if the current is flowing this way, the magnetic field would be up inside the loop. Okay, and that would be counterclockwise. Okay, so just have to line your thumb up with the direction of the current, and then you get the magnetic field that way. And you just have to try it and see which one works. Okay, and then now we can calculate the magnetic field due to current. So if you have a long straight wire, it's called, the magnetic field is measured in Teslas. It turns out to be mu zero. That's how this is pronounced. Mu zero I over 2 pi r. And mu zero is the permeability constant. So 1.26 to the minus sixth Tesla meters per amp. Okay, we had epsilon naught with electricity. Now we have mu zero for magnetism. And we'll see mu zero and epsilon naught turns out to be related to the speed of light. We'll see that not today, but coming up in this chapter or the next chapter. Actually, chapter 25. Regardless of that, this is the strength of the magnetic field due to just a long straight wire. So unless they tell you otherwise, which they won't, we are dealing with long straight wires. As long as the wire is 14 times bigger than the distance from it, we have a long straight wire. This is good. This formula is good up to 99%. So we'll always have this situation if it's a long straight wire. This is the strength of it. mu zero, I is the current flowing through it, r is the distance away. So if you have a long straight wire, this is the magnitude of the magnetic field, the direction you get from the first right-hand rule. Okay, so don't forget what this constant is too. Here are some typical magnetic field strengths actually. 10 centimeters from a 1 amp wire, 2 times 10 to the minus sixth. Surface of the Earth, this is the Earth's magnetic field strength, 5 times 10 to the minus fifth. Now if you're 1 centimeter away from a 10 amp wire, you have 2 to the minus fourth. This is over 10 times, this is about 10 times bigger than the Earth's magnetic field. Refrigerator magnet, about 100 times bigger than the Earth's magnetic field. And then here's some other typical values. 100 turn coil, 1 centimeter in diameter. We have this strength. Surface of the sun in a sunspot. This is really huge. I mean, it looks like it's small because it's the -1 power, but it's just the units that we're using. Rare earth magnet or a MRI solenoid, 1 Tesla. So really, really, really strong. So if you ever get an MRI, you're in a magnetic field that is like 100 times bigger, or sorry, 10 times bigger than the magnetic field of the sunspot. Okay, so here's a magnetic field. Here's a wire. The current's going into the wire. Here's the direction of the magnetic field, and then we have the formula to calculate the strength. And if you were to plot it, it looks something like this. It goes like 1 over r. A lot of things in physics go like 1 over r squared. This is like 1 over r. So it does drop off. Just it doesn't drop off as quickly as, say, the Coulomb force law or something. So if you're twice as far away, the force is half as much. Okay. Now if you have more than one source of magnetic fields, you can add them together to get the net magnetic field. So we won't be doing a lot with bar magnets and wires together, but you might have a situation where you have a long straight wire and a loop hooked together. Regardless, you have to take the contribution from the bar magnet, add it to the contribution from the other source. In this case, it's current going out of the wire, and you can figure out the net magnetic field. Now, if you have a current loop, the magnetic field right in the center is mu 0 I. This is the same mu 0 we had before. So mu 0 I divided by 2r. And that's the magnetic field right in the center of a current loop. Same thing, you get the direction of the magnetic field from the right-hand rule that we did before. And then you get the magnitude of the magnetic field right in the center from this formula. And then r is the radius of the loop. Okay, so that's the second scenario where you can calculate the magnetic field. What if you have more than one loop? So these are not, this is not a solenoid. This is several loops, not all just packed together. This would be like a single flat coil. It doesn't have a shape. Like a solenoid would be spread out. This is just a loop, really a single flat coil, but it might have a couple more turns or loops, in other words. It's just, it doesn't have a length to it. That's anything too great. Okay, so again, right in the center, mu 0 I, and and then we have an n here. N is the number of loops that you have. Same thing divided by 2r. Okay, so we've got current loops, and there's multiple ones. How do you not know it's a solenoid? Well, they would tell you that it's a current loop with this many turns, or the other case, they would say it's a solenoid, because a solenoid then has a bigger dimension than this. Okay, here's an example. Green turtles are thought to navigate by using the dip angle of the Earth's magnetic field. To test this hypothesis, green turtle hatchlings were placed in a 72 centimeter diameter tank with a 60 turn coil of wire wrapped around the outside. A current in the coil created a magnetic field at the center of the tank. Okay, so you have a tank, you have 60 turns of wire wrapped around the outside, and you provide a current, and you want to try to cancel out the Earth's magnetic field component that's vertical to this. So basically, the loop is going to produce a magnetic field one direction. You want to cancel out the Earth's magnetic field that's in the opposite direction, and we want to know how much current that has to be. This dip angle comes into play because that has a horizontal and vertical component, and from this dip angle we can figure out the vertical component. So basically, you're kind of messing with the turtles. You're canceling out the vertical component of the magnetic field to see what happens, to test the hypothesis. Okay, so here's the Earth's magnetic field here. Now the dip angle is measured from the horizontal down, and that's 60 degrees in this problem. Okay, and then here's the coil. Current's coming out at you, and then it's going back in here, and there's a certain amount of turns there. So this coil is going to produce a magnetic field that's up. Use the right-hand rule, and you'll see that. And we want to cancel out this part of the Earth's magnetic field that's down. So if this is 60 degrees, this turns out to be 60 degrees down here. That's 30 degrees. We'll have to use a little bit of trig to figure out the vertical component of the Earth's magnetic field, and then we know how much this is. We can figure out how much current we need to get the same magnitude that's up. Okay, so here's the Earth's magnetic field. They tell you it's 50 microteslas, so 50 times 10 to the minus 6 teslas. Sine of 60, that will give you the vertical part. So again, if this is 60, this is 60, this one here. So the sine of 60 would be this side over this side. So the sine of 60 is the vertical component over the total amount. Do a little bit of algebra, and that's where this is actually coming from. Okay, so 4.33 to the minus fifth, the minus sign just tells you that it's down. Now we need to have a magnetic field because of this coil that has this same magnitude. And then here's the formula for the magnetic field for a coil. U0 Ni over 2R. That's what B is. We want the current that goes along with that. So do a little bit of algebra and solve for the current. So you have this. Whoops. Sorry about that. You've got this formula here. Solve for I. So multiply both sides by 2R, divide both sides by mu0 n, and you have this formula. You could plug in the radius of the circle, but then you're multiplying it by 2, so you might as well just use the diameter. 2R is the diameter. That's why you see the diameter here. And then you have mu0 and 60. So 0.41 amps. That's not a whole bunch of amps. You could cancel out the Earth's vertical component if you just had a half of an amp running through this scenario. Okay, excellent. So that equation shows the field is at the center of the coil, proportional to the number of turns. So if you have more turns, you have a bigger magnetic field. Okay, so this that table that we saw, 0.01 for the field at the center of a 100 turn coil. That's 1 centimeter diameter, carries 1 amp. So it makes sense. This is what this slide is telling you. The number that we actually calculated makes sense. It's not some outrageous number. It's in the ballpark from what you saw before. Okay, so this one is about 100 times larger, carries about half as much current. So those effects balance out. Solenoid, the field inside is fairly uniform. The field outside is very small, so we're concerned about the magnetic field inside the solenoid. It can be built quite large, miles and miles of wiring, actually. And here's the formula for the magnetic field inside a solenoid. Mu 0 N is the number of turns, I, divided by the length of the solenoid. So you don't see the radius of the solenoid here. The radius doesn't come into play at all. It's mu 0, I, and then times N over L. So N over L is sometimes called the turns ratio, this thing here. So sometimes problems will just give you N over L right away. They'll say it's like 1,000 turns per meter or something like that. Okay, so just be careful. Sometimes N over L is just given to you as one number. Okay, and this is the magnetic field inside the solenoid. Okay, it might look something like this. Here's the length of the solenoid. N is the number of turns. Mu 0 is just a constant, and I is whatever the I would be. Same thing, magnetic fields measured in Teslas. Okay, let's take a look at this. Solenoid 2 has twice the diameter and twice the length and twice as many turns. How does the magnetic field of this one depend with the magnetic field of that one? Well, it doesn't matter the diameter being twice as big. The diameter is not in the formula. Solenoid 2 down here has twice the length and twice as many turns. But that means it has the same turn ratio. N over L is the same. This N over L of the one down here is the same as N over L over here. So if they both have the same current, they're going to have the same magnetic field. Turns ratio is what matters. N over L matters. And if it's the same, the magnetic field is going to be the same if the current is the same. Okay, same turns ratio, same magnetic field strength. Okay, here's another example. A typical MRI has a length of about 1 meter and a diameter of 1 meter. A typical field inside the solenoid is about 1 Tesla. How many turns of wire must the solenoid have to produce this field if the largest current is 100 amps? Okay, so they're giving us 1 Tesla for the strength. They're giving us 100 amps. The diameter of 1 meter, this doesn't matter. The diameter doesn't come into play. But they are giving us the length. Okay, so from this we should be able to calculate the amount of turns. Okay, so we have the formula. Not very long compared to its diameter, so we could use that equation. There won't be a case where they try to trick you and you have to say, no, I can't use that formula. This is what we have. Okay, so 1 Tesla, 100 amps, length 1 meter. We'll have to take our equation, do a little bit of algebra to it. So this comes from B was equal to mu 0 I N over L. Solve for N, you get this. So again, you'd have B is equal to mu 0 I N over L. Do the algebra. N turns out to be LB over mu 0 I. And put everything in here. And you can see how the units work out. Here's a Tesla. Whoops. Cancels with this Tesla. You got a meter and a meter that cancel. Amp and amp that cancel. So really we're left with no units. Turns aren't really units. They're just an identifier of how many things we have. So it's a counting thing. So you get 8,000 turns. So that's a huge amount of turns. 8,000 turns in 1 meter. Okay. It's quite large, but the field is also really large, right? 1 Tesla is a huge magnetic field, so you need 8,000 turns to do that. Okay, so it makes sense what we have here. Now, if you were to go back and figure out how long the wire is, you might find out that you need like miles of wiring. Okay, so here's a little summary of what we have to work with, what we could actually calculate. We have a long straight wire here. Here the current's actually coming out at you, so the field's wrapping around. And here's the magnetic field strength a certain distance away from the wire. U 0 I over 2 pi r. And r in the formula is the distance away. And there's what mu 0 is. We have a current loop, and we can calculate the magnetic field right in the center. mu 0 ni over 2r. Now, if it's just one loop, the big N here is just 1. To get the direction of the magnetic field, same thing, you use the right-hand rule, and then you can calculate the magnetic field right in the center of this current loop. And then finally, we have a solenoid, which actually has some length here. And we calculate the magnetic field in the center. I shouldn't say not right exactly in the center, but inside here, anywhere inside here. Here's the magnetic field strength. Just be careful, you do not need the radius of this. You just need the turns per length ratio. Here's an example we can take a look at. What is the direction and magnitude of the magnetic field at point P in the center of the loop? And this one is similar to 24/7 on the current homework.
Okay, actually it's similar to 2417 on the homework. So we've got current flowing to the right in the long straight wire, and then the current also goes around the loop here. So there's going to be a contribution to the net magnetic field because of the long straight wire and also because of the loop. So let's take a look at that. There's the long straight wire part, 3 amps to the right, and then it enters the loop and goes around. So if you look at the center of the loop, right in the center, if you use the first right-hand rule, because of the long straight wire, the magnetic field's into the page. And because of the loop part, same thing, put your thumb in the direction of the current, the magnetic field's into the page. So the net magnetic field is the magnetic field because of the long straight wire plus the magnetic field because of the loop. So LSW means long straight wire. Okay, so we'll have to write down the formula for the long straight wire. Mu 0I over 2 pi. And in the formula, it's little r. That's the distance from the wire to the point. What happens in this problem that is still the radius of the circle. So it's going to be big R. In the formula, it's little r, but little r and big R are the same thing here. Plus the magnetic field because of the loop, and it's just one loop. So we've got the formula for that, mu 0I over 2r. And then r is the radius of the circle. So we know what mu 0 is. It's just a constant. I is given in the problem. R is given in the problem. So it's just up to you to put the numbers together. Now, just be careful. The radius is given, but it's given in centimeters. You'll have to convert that to meters to actually solve the problem. Okay, if you have any questions, just email me, and I'll talk to you soon. Well, maybe if you send me an email. Okay, bye-bye. Have a nice day.